Hi student, welcome to chemistry class with Emerald. In this class today, we are going to be looking at energetics, and we are going to look at what energetics is, enthalpy changes relating to breaking and formation of bonds, standard enthalpy changes, experimental determination of enthalpy changes by the calorimetry method, Hess's law, and calculation involving standard changes of reaction. This video is brought to you by Agota Virtual Learning. Now let's look at what energetics is. Energetics is the study of energy changes associated with chemical reactions. During chemical reaction processes, there are different changes in energy, sometimes from potential to kinetic, but mostly chemical reactions are always involved with energy changes in form of heat. Therefore, there is a term we use called thermochemistry. Thermochemistry is the study of heat changes associated with chemical reaction. Basically, is under a general term that we use called thermodynamics. That studies generally heat changes in substances. So, having said that, let's also look at key terms. In a typical chemical reaction, we have what is called the container, the surrounding, and the universe. A chemical vessel or a chemical apparatus might be the container. Now, in the container, you have what is called the surrounding, and then anything outside the surrounding is called the universe. So there are a lot of chemical heat changes that are being exchanged. Basically, two things are exchanged in a typical chemical system. In a typical chemical system, you have heat and matter, or energy and matter, that is being exchanged. And that is why in thermodynamics, we have what is called an open system, where both energy and matter are exchanged with the surrounding. We have a closed system where you have either energy or matter being exchanged with the surrounding. And then we have an isolated system where neither energy nor matter is exchanged with the surrounding. So in thermodynamics generally, we have a system, we have the surrounding, and we have the universe. Any environment, in the immediate environment of a system, the system can be a container. The immediate environment of the system is called the surrounding. So anything outside that surrounding is called the universe. Then there are some basic terms we use in energetics, or generally a chemical system is defined by three major things. Number one is the enthalpy of the system, which is the heat content in a particular substance. We have the entropy of a system, which is the degree of disorderliness or randomness of a system. And then we have the free energy, which is the fraction of the system that does useful work. We have two types of free energy. We have the Amos free energy and the Gibbs free energy. But at this level, we usually look at the Gibbs free energy. So the Gibbs free energy generally is the fraction of the system that does useful work. Enthalpy is denoted by H, and then when there are changes, because all three of them are state function, that means they depend on the initial and final state of the system. So enthalpy change is given as delta H, entropy delta S, and the Gibbs free energy delta G. Then for enthalpy of a enthalpy change, we have the heat content of the product, HP, minus heat content of the reactant, HR. This is the formula we use for it. So generally speaking, in energetics, It has to do with energy changes, biochemical reactions. Thermochemistry is study of heat changes, and then we have talked about enthalpy. Now let's move. All of these follow a typical law, which is one of the foremost law in chemistry, and it's called the law of conservation of energy or mass. But in this case, we are looking at energy. The law of conservation of energy states that energy can neither be created nor destroyed. It's also the first law of thermodynamics. That means that energy can only change from one form to another. This law gives us a background study of what actually happens in a chemical reaction or in a chemical system. No energy is lost in a chemical system, but energy is moving from one form to other, or from the reactant to the product, or the product to the reactant, as the case may be. Now, we look at the internal energy and the enthalpy. Don't forget, enthalpy is the heat content of a substance or a chemical system. The internal energy is the intrinsic energy of that system. Intrinsic means the energy content of the system. Each reaction or each chemical substances have their energy content, which is the intrinsic energy. And of course, this usually have a major role to play in the heat content of the substance. For instance, you check this reaction. That's a displacement reaction between zinc and a dilute mineral to produce zinc chloride and H2. You observe that at constant volume, the level of hydrogen, or the level of the gas produced, is lower. But you now compare at constant pressure, where the level of gas is higher. Now, this tells us about the relationship between the internal energy of that system, the heat content of that system, and especially the work done against atmospheric pressure that is within the surrounding of that system. Now, what do we mean by this? There is a relationship here. The heat change at constant pressure is equal to change in internal energy plus work done on the surrounding. The heat change, which is the enthalpy of a system at constant pressure, will be determined by the change in internal energy of the system and the work done on the surrounding. That's the relationship between them. Now let's look at a more interesting part. But this one leads us to what we call the exothermic and the endothermic reaction. An exothermic reaction is a reaction in which heat is liberated or released to the surrounding. Heat is liberated or released to the surrounding. Here, the enthalpy, delta A, enthalpy change is equal to minus V. That means the heat of the product is greater than the heat of the reactant. And of course, this is a energy profile diagram of the reaction. For endothermic reaction, the is a reaction in which heat is absorbed from the surrounding. Here delta H is plus V, and the heat of the reactant is greater than the heat of the product. Now you observe that in exothermic reaction, it is hotter than the surrounding. That means the system is hotter than the surrounding, while in endothermic reaction, the system is cooler than the surrounding. Okay, so let's look at how this relates with breaking and forming bond. How does it relate with forming and breaking and forming bonds? In a typical combustion reaction, that involves methane, which is an alkane, a saturated hydrocarbon being undergoing combustion to produce CO2 and water. You will observe that in the energy profile diagram, of course, you have the reactant, then the reactant moves to acquire activation energy and then reaches an activated complex where it transitioned to the product. Now, the energy required to break the bond is at the reactant side, and you have a carbon covalently bonded to four hydrogen atom in a tetrahedral shape, and then you have two oxygen molecule, which are they are also covalently bonded to one another. And then at the activated complex, this is how they are orientated, and this is how they form. And then as they move to the product, energy is also released. So energy is released to break the bonds so that they can move to the activated complex, and then energy is also released as new product, which is CO2 and H2O, are being formed. Now, what's the implication of this? So, in a typical exothermic reaction, the energy that is required in breaking the bond in the reactant is less than the energy released in forming the bond. What do we mean by that? So in a typical exothermic reaction, products contain stronger bond, and because the energy to break the bond in products is higher, therefore the heat content of the products will be greater than the heat content of the reactant for an exothermic reaction. The heat content, because the energy required to products contain stronger bonds, so the energy required to break the bond in the product are higher than that of the energy required energy required to form bonds in the product are higher than energy required to break bonds in the reactant. So the heat content of the product is greater than it. So for exothermic reaction, HP is greater than HR. And we can see for an endothermic reaction, for instance, we have nitrogen molecule which contain a triple bond, covalently bonded with oxygen to now form a 2NO2. That means N2 plus 2O2 to form a 2NO2, 2NO2 respectively. Energy required to break the bonds from here so that they reach activated complex and then they form the bond. What are we saying? For an endothermic reaction, the energy required to breaking the bonds is more than the energy released in forming the bonds. What do you mean by that? Reactants contain stronger bond. In endothermic reaction, reactants contain stronger bond. That means that the heat content, that's the enthalpy of the reactant, HR, is greater than that of the product. For endothermic reaction, HR is greater than HP for endothermic reaction. Now let's look at standard enthalpy changes. All reactions have their standard enthalpy changes, which are determined experimentally, usually by what is called a calorimetric method. So each of them have, and then we call something thermochemical reaction. A thermochemical reaction is a reaction in which the heat content value or the enthalpy of that reaction is known or given or unwritten in the equation. This is a typical example. What you just put after the equation, just put semicolon, then delta H is equal to whatever it is. So it's showing the heat content or the enthalpy change of that reaction. That type of reaction is known as thermochemical equations. Okay, so let's look at standard enthalpy changes. As enthalpy changes depend on temperature and pressure, it is necessary to define standard states and conditions. Like we have said, enthalpy, entropy, free energy are all state function. They depend on the initial and the final state of a system. So for standard enthalpy changes, there are three factors that affect that standard. So for a standard enthalpy change, it must occur at 1 atm and a pressure of 1 atm, a temperature of 25 degrees Celsius, and then the elements or the compound in their normal physical state. So the conditions for a substance to meet to undergo standard enthalpy change is that the elements of the compound must be in their normal physical state. There must be a pressure of 1 atm and the temperature of 25 degrees Celsius or 298 Kelvin. So when enthalpy change are under standard condition, they are given as delta H theta, H to power theta. This is standard enthalpy change. Okay, so in defining standard enthalpy changes, we begin to look at enthalpy changes of reactions. Here we are going to look at the standard enthalpy changes of neutralization, combustion, solution, and formation. So let's look at the standard enthalpy change of neutralization, or heat, or what we call the heat of neutralization. Delta Hn is the enthalpy change when 1 mole of water is formed from the neutralization of an acid by an alkali under standard condition. Standard enthalpy change of neutralization or heat of neutralization is the enthalpy change when 1 mole of water is formed from the neutralization of an acid by an alkali under standard condition. Of course, you know that an example is when you have a neutralization reaction. An example is when you have HCl being neutralized by NaOH to form NaCl and H2O. There is H plus coming from the acid and OH minus coming from the base. If they combine together, they form water. So the heat of neutralization for a standard enthalpy change of neutralization, it has been determined experimentally, and this is minus 57.3 kilojoules per mole. What it means is that a typical neutralization reaction is an exothermic reaction. A typical neutralization reaction is an exothermic reaction. Okay, so let's look at some of the values. Like I said, it has been experimentally determined. Let's look at some of the values when there is reaction here. Again, observe that for a strong acid and a strong base, it is usually minus 57.3 for strong acid and strong base within that range. But you can have a strong acid and a weak base, or a weak acid and a strong base. Those ones varies accordingly. Okay, so again, let's look at standard enthalpy change of solution, which is the enthalpy change when 1 mole of a solute is completely dissolved in a sufficiently large volume of solvent to form an infinitely dilute solution under standard condition. In solubility, we said solute plus solvent is equal to solution. So, and of course, again, observe something. We can also say heat of solution, which is standard enthalpy change, is the heat liberated or absorbed when 1 mole of solute is dissolved in a sufficiently amount of solvent. Now, what do you mean by that? Is that the heat of solution of a reaction can be exothermic or endothermic, depending. For instance, if you dissolve sodium hydroxide in water, what you are going to have is an exothermic reaction. The container will be hot. And so that kind of reaction is an exothermic reaction. But when you dissolve copper sulfate in water, the environment will be cold, or the container will be cold. That means it's an endothermic reaction. So note that heat of solution can be exothermic or endothermic. How do you know this in question? Yeah, the question is going to state specifically, maybe there is a raise in temperature when the dissolution occur, or there is lowering in temperature. If there is a raise in temperature, that means an exothermic reaction. But when the temperature is lower, that means That's an endothermic reaction. Kindly take note of this. Now let's look at enthalpy change of solution. For instance, sodium chloride being dissolved in water. You observe what I've said the other time. The delta H is plus 3.9 kilojoules per mole. That means that is an endothermic reaction here. And when you dissolve normal salt in water, this is what you get. But when you dissolve lithium chloride in water, it is negative 30 minus 37.2. That means here is an exothermic reaction. You can study the energy profile diagram on your own. Now, the standard heat of solution, these are heat of solution of some substances. You observe that sodium hydroxide, which is a base, is negative. That means it's exothermic. NaCl, which is a normal salt, is endothermic. KOH is exothermic, and KBr is endothermic. Now let's look at standard heat change of formation, which is the enthalpy change of reaction when one mole of a compound in a standard form or standard state is formed from its constituent element. Formation is generally when you have two elements combining together to form a compound. The heat change that accompanies this type of reaction is called, the standard heat change that accompanies that of reaction is called standard heat of formation. Also note again that it can be exothermic or endothermic. You see here, when sodium combined with chlorine to form sodium chloride, this is negative. But in some cases, it can be positive. Again, note that when the heat change for an element or a molecule is equal to 0, any chemical substance in its elemental or molecular state have a heat change of 0. Please take note of that. Now, we also have a standard heat change of combustion. Is the enthalpy change when one mole of the substance burn completely under standard condition. They burn under, so when a substance undergo combustion, the heat change that is accompanying it is called heat of combustion. But when it occurs in standard condition, we call it standard heat of combustion. Of course, it's going to be typically exothermic because all combustion reactions are exothermic. That one take us to neutralization is exothermic, combustion is exothermic. Solution and formation can either be endo or exo respectively. Okay, so let's look at all of this on it. So you see that when hydrocarbons undergo combustion, they produce CO2 and water respectively. These are heat of combustion. You notice that they are all negative, yes, because combustion is exothermic. The experimental determination of enthalpy changes is by calorimetry method, and that involves the use of a calorimeter. A calorimeter is a container used for measuring temperature change of solution. For combustion, we use what is called a bomb calorimeter. Okay, so we determine the enthalpy change of neutralization. This is the setup. We have the reaction mixture, you have the container, you have the stirrer, and the temperature, the thermometer to measure the temperature. Then when you stir very well, and then of course there is a polystyrene cup, a polystyrene board, and that's you can measure the temperature from here. I'm trying to be a bit fast. So in that reaction that we have seen, like that setup, the heat that is liberated, since is neutralization, so we are focusing on the heat evolved. Is equal to the mass of the solution plus the specific heat capacity of the solution, then plus the mass of the calorimeter and the specific heat of the calorimeter plus the temperature change. So typically, the quantity of heat produced here, Q, is equal to MC theta or MC change in theta, as the case may be. If it is calorimeter and the solution, we are going to do it separate. M1, C1, M2, C2, change the temperature. But if it's a singular one, which we usually use in calculations, we can also have what is called MC theta or MC change theta. That means if there is a change in temperature in the process. Okay, for combustion, this is how it is being set up. For combustion, this is how it's being set up. Ethanol is used, or spirit lamp, and so on. You can set it up like this, and then the heat also involved is also this. The heat involved is this. For solution, you are going to have a M1C1, M2C2, delta T. By measuring the temperature change when a known mass of solute is added to a known volume, this is what you get as the heat change. Because it can be endo or exo, so we are not using heat involved here. So for formation, the enthalpy change of a formation of a substance can be quite high because it will require a lot of breaking of bonds and forming of new bonds as well. So it is found out basically using Hess's law of constant heat summation. So what is Hess's law? Hess's law of constant heat summation states that the total enthalpy change accompanying a chemical reaction is independent of the route by which the chemical reaction takes place. So what we mean is that irrespective of the part taken by a chemical reaction, the total energy change is independent of it. You will check here that when you want to produce A plus B, they have an intermediate which is C plus D to now finally form E. Irrespective of how it is taken, Hess's law said that the heat change is independent of the part taken or the route taken by that reaction. Now, what's the implication of this? We can use Hess's law to generally relate substances together in terms of enthalpy changes of reactions. We can use Hess's law to relate together in terms of enthalpy changes of a reaction. Okay, look at from graphite, which is an allotrope of carbon, to CO2, where they undergo oxidation. You will see it will first form CO, which is, and then move again to now form CO2, as the case may be. So, irrespective of the route, the total enthalpy changes is still the same, irrespective of the route that is being taken. Okay, so you can also see this, the Born-Haber cycle, how it shows that this is your reactant, this is in the intermediate, and then this is the final. Then the reactant can form final or can form intermediate, depending on how the reaction is. But irrespective of this route, the heat change remains the same. Okay, so let's look at the importance of Hess's law. The enthalpy change of some chemical reaction cannot be determined directly because the reaction cannot be performed in the laboratory. The reaction rates are too slow, and the reaction may involve formation of side products. But the enthalpy change of such reaction can always be determined indirectly by applying Hess's law. So generally, Hess's law can help to understand the heat change or enthalpy change of some complex reaction, which are reactions that cannot be performed in the laboratory, or the reactions are slow, or they require formation of side products. Hess's law can be applied to be able to know their heat changes. You can see the enthalpy change of formation of CO when C reacts with oxygen, that's carbon in form of water, react with oxygen to form CO, and then finally to CO2. And this is the final enthalpy of formation of the final enthalpy of that reaction minus 110.5. We can have the enthalpy of formation of CaCO3 too when calcium reacts with graphite and then with oxygen as well. Okay, so when you are calculating the standard enthalpy change of reaction from standard enthalpy changes of formation, it is possible to calculate it in that form. So for standard enthalpy of reaction, the heat of formation of the product is equal to the heat of formation of the reactant. So if you want to calculate standard enthalpy of reaction, the HF of the product is equal to HF of the reactants. And you can also calculate the the standard enthalpy change of formation from combustion. For HF, the HC of product minus HC of reactants. Okay, let's look at some calculations. Now, the enthalpy change of the following reaction under standard condition is minus 566.0 kilojoules. This is the reaction. CO plus O2 to give 2CO2. What is the total enthalpy change of combustion of carbon monoxide? Standard enthalpy change of formation. Now, this is a typical combustion reaction. CO undergoes combustion to form CO2. However, the standard energy change, which is delta H, has been given. So we are looking for AC, but we can calculate AC from HF. Now, to calculate this very well, look that the standard enthalpy change of combustion is of CO will be that of the standard enthalpy change, and then the oxygen that is there. If you check very well that when you have 2CO and then O2, CO is generally half in this case. What do we mean by that? If you check very well, we are looking for standard heat change of combustion of carbon monoxide. So the energy that is required, the O2 that is required is half. If you check, if others are 2/1, that means for the energy required there will now be half, which is 1/2, the inverse of it. So that's why we're having 1/2 of the standard enthalpy change. So the standard enthalpy change of combustion of CO is going to be half of the standard enthalpy change. So that's why we're having 1/2 multiplied by 566.0. So the answer is minus 283.0 kilojoules. Now let's look at another one. What term may be given for the enthalpy change of the following reaction? We have N2 plus O2 to give NO2 gas. So the answer is the energy change of combustion of nitrogen. Is the name given here, the enthalpy change of combustion of nitrogen, because of it undergo combustion. So the enthalpy change of combustion of nitrogen, or we can also call it the enthalpy change of formation of NO2. So NO2 is formed by N2 plus O2. Then N2 undergo combustion to produce NO2. So these are the two names that which you can give them. Okay, let's look at some more complex problems. The question says determine the enthalpy change of neutralization of 25 centimeter cube of 1.25 molar hydrochloric acid and 25 centimeter cube of 1.25 molar sodium hydroxide solution uses the following data. You have given mass of calorimeter to be 100 gram, initial temperature 15.5, initial temperature of alkali 15.5, final temperature of reaction mixture 21.6, and then you are given specific heat capacity of both water and calorimeter to be 4.4200 and 800 joule per gram per Kelvin respectively. Now to solve this kind of reaction, we assume that the density of the reaction mixture is the same as that of water and is given as 1 gram per centimeter cube. So to calculate the mass, you can also actually calculate mass from volume. Don't forget that density is equal to mass over volume. Then that means mass will now be equal to density times volume. So from here we can multiply the volume multiply by the multiply by the density to give us mass, which is 50 gram. Don't forget that from the question, both of them are having the same volume. So if they have the same volume, they are expected to have the same density. That's why we are using 1 gram in this case. So if they have both of their volumes together multiplied by the density, it will give us the mass, which is 0.05 kilogram. It is 50 gram divided by 1000 to give us the kilogram. Then the heat that is given out in this reaction is M1C1, like we have done from the experiment, is equal to M2 plus C2 theta change, that's temperature change. So 0.05 multiplied by 4200 plus 0.1 kilogram multiplied by 800 times temperature changes. Times temperature changes. Please don't forget, you may be asking, why are we using 0.1 kilogram? Now, the mass of calorimeter has been given. It's only that the mass of solution was not given. That's what we got. So the mass of calorimeter is 100 grams. If you divide by 1000, it gives you 0.1. So this is the mass of the calorimeter that was given. The mass of calorimeter multiplied by the specific heat capacity of the calorimeter. Then the mass of solution multiplied by the specific heat capacity of water there. So please take note. And so that one give us the H here is 1.1769 joules. And then for a typical neutralization reaction, let me also give you another formula that can help you. Delta H is equal to Q over N. Delta H is equal to Q over N. That's another formula for heat of neutralization. Q is the quantity of heat that has been given here. This is our quantity of heat, 1769 joules. Then N is the number of moles. So to find the number of moles, simple, of both acid and base, we can say number of moles is equal to CV. That's concentration times volume. Concentration times volume. Of course, the volume must be in dm cube, and that is why you are seeing 25. That's 25 over 1000. That's why you are seeing 25 multiplied by 10 raised to the power minus 3, and the concentration of both of them has been given as 1.25. So concentration times volume here will give us a number of moles. So the number of moles of water that is now formed will now be 0.03125 because they are coming from H plus and OH minus to give HU. So the number of moles of water formed here is 0.03125 mole. Then we can now find our H. Our H therefore is equal to delta H is equal to Q over N. So that's the quantity of heat that is being produced over N. So we can immediately convert, or you wait for the final answer before you convert, because delta H is given in kilojoules per mole. So if you do 1769 over 0.03125, it will give us 56608 joule per mole here. So if you convert it to kilojoules, you are going to have minus 5.66 kilojoules per mole. Don't forget, delta H is equal to Q over N. The first thing is to find Q, then find N, and then you can find your delta H, as the case may be. So this is very important. Let's look at another question that involves combustion. Again, delta HC in a simple formula is equal to Q over N as well. So another thing is to find your Q, find your N, and then you can find your delta HC. We have the mass of spirit lamp before experiment. We have mass of spirit lamp after experiment, mass of water in water calorimeter, mass of copper calorimeter without water. These are the information that was given. Then you go back to the normal formula that we use, M1C1 plus M2C2, T changes. So you can, from here now, you should be able to find your, what's it called? Your M1 given there. Check very well. You were given mass of water to be 50 gram. So you divide by 1000. That's 0.05 kilogram. Multiply by specific heat capacity of water, which is 4200. Plus the mass of copper calorimeter now, which is 380 gram divided by 1000. That's 0.38 kilogram. Plus specific capacity of the calorimeter, and then the temperature change that occurs there. So your Q here is 21067 joules. Like I said again, you are still going to look for the number of moles. Now the mass of ethanol that was burnt here now will now be, one was born, mass of spirit lamp is before the experiment was this, but because it's undergo combustion, the mass of the spirit lamp that was remaining is this. That means the mass of spirit lamp that actually was burnt is 45.24 minus 44.26. That's what you should. So the mass of ethanol burnt therefore will be 0.78 gram. So the number of moles of ethanol burn will now be mass over molar mass, which is 0.78 over 46.0. The molar mass of ethanol, which is C2H5OH, is 46.0 gram per mole. So you are going to have number of moles here to be 0.017 moles. So you have gotten Q and you have gotten N. So delta AC is equal to Q over N. Like I've said, it will give you 1239235 joules per mole. If you convert to kilojoules, you are going to have 1239 kilojoules per mole. But because delta AC is endothermic, that's heat of combustion, you now put negative. That's minus 1239 kilojoules per mole. These are to solve this question. Let's take another question on the heat of solution. 0.02 mole of anhydrous ammonium chloride was added to 45 grams of water in a polyethylene cup to determine the enthalpy of solution. It is found that there was temperature drop. Take note of that. Temperature drop means that the reaction is endothermic, not exothermic. But if there was temperature raise, that's exothermic. Take note of that. Look at the information given here. We can solve for heat of solution. It's still delta HS is equal to Q over N. Now we can find our Q, which is quantity of heat that is absorbed. Now in this case now, our C2 heat calorimeter is not present, is 0. We only have a MC theta change here. There is no calorimeter here, so you are going to use MC theta change. Mass is M is the mass of water. C is specific capacity of water. Then the delta T is change in temperature. From there, you are going to get your Q, and then Q is equal to delta H is equal to Q over N. That's 0.234 gram over 0.02. Now, it's supposed to be 0.284 kilojoules. 0.284 kilojoules over 0.02 mole, and it will give us 14.2 kilojoules per mole. But note that we are going to add positive because it's an endothermic reaction. That's why we have 14 plus 14.2 kilojoules per mole. Final one, we can look at this question like this. We are given a thermochemical equation like this. The now said is the reaction endothermic or exothermic. What is the enthalpy change for the following reaction? We look at them, and then if the enthalpy change for reaction is plus 41.1, calculate the delta H for this. Now the reaction is exothermic because it's a combustion reaction. Any reaction that involves O2 is a combustion reaction, is endothermic. Then the second question that was asked is that what is the enthalpy change for the following reaction, the 1 and 2? This is determined experimentally, and it is 5 plus 571.6 kilojoules. The second one is minus 285.8 kilojoules. And then the third one, we can use Hess's law to determine this. That's 2H2 plus O2. Of course, from what we have seen here, from the first one here, minus 571.6 to give us H2O liquid. And then since it's H2O liquid, if you check very well, it gave us the first one gave us this. The second one produces plus 41.1 kilojoules. Then according to S law here, we just multiply it by 2. So it will give us our answer. So the final answer is minus 571 plus 2 times plus 41 kilojoules to give us minus 489.4 kilojoules per mole. So let's look at some WAEC questions. WAEC 2020, in an equilibrium reaction between two gases Q2 and R2 to form QR. The energy content of the reaction is 100 kilojoules and that of the product is 54 kilojoules. The energy content of the activated complex is 210 kilojoules. You are expected to draw an energy profile for the reaction that will determine the activation energy for the reaction, the enthalpy change. Then you have to write a balanced equation for the reaction and state whether the reaction is exothermic or endothermic. Can you attempt this question? Let's see how you, from what we have said so far, let's see how you are going to attempt the question. Okay, let's look at it together. This is the energy profile diagram for that reaction. Don't forget the question says the two gases Q2 and perform QR. That means Q2 plus R2, and the product is QR. So in the reactant side, you are writing Q2 plus R2, the product are having QR. The energy content of the reaction of the reactant is 100 kilojoules. You can see here, but it moves from 100 to what? And that of the product is 54 to 54. You will see there. Then the activated complex is 210. So this is the energy profile diagram for that reaction. Now let's check the activation energy. For you to calculate activation energy, you just move from the activated complex to the reactant. It is, you trace to activated complex, which is 210, to that of reactant, which is 100. So 210 minus 100 is equal to 110. So the activation energy required is 110 kilojoules. For the enthalpy change, that's the heat of product minus heat of reactant. Why? Because the energy profile here is for exothermic reaction, because the heat of the product is greater than the heat of the reactant. Please take note of that. Take note of that. So you have HP minus HR, which is 54 minus 100, that's minus 46 kilojoules per mole. The equation is Q2 plus R2 to give 2QR, and the reaction is exothermic. That means delta H is negative, or HP less than HR rather. Sorry, our HP is less than HR. If you check very well, HP is less than HR for exothermic, while HR is less than HP for endothermic, and heat is liberated. You can put it that way as well. Let's look at another calculation. Given a standard heat of combustion of butane to be plus 588 kilojoules per mole, calculate the heat of combustion of 14.5 gram of butane. If you see this question in exam, can you show how you are going to solve it? Show how you are going to solve it. So let's wait for you for some seconds to solve. Now, if you have been able to solve, this is what you're going to get. The molar mass of butane is 50 gram per mole. Amount of butane in moles, therefore, will be mass over molar mass. That's 14.5 over 58 to give you 0.25 moles. If 1 mole of butane is plus 5877 kilojoules per mole, then 0.25 moles will be 0.25 times 5877, and that is plus 14,1469 kilojoules per mole. You can solve it that way. Alternatively, you can say 58 gram of butane, which of course you know that we can relate molar mass and mass. So that means the mass of butane here is 58 gram. If it produces plus 5877 kilojoules of heat, then 14.5 gram of the same butane will produce X. If you cross multiply, X is plus 1469 kilojoules respectively. Now let's take another question. He said, how much heat will be liberated if 8 gram of hydrogen bonds in excess oxygen according to this equation? Now, in this question, you are looking for Q. Take note, in this question, you are looking for Q. And then don't forget delta HC or HS or HN is equal to Q over N. And here we have been given delta H. So what we are looking for generally is N, so that we can be able to solve it. To solve the question here, I think I will give you some seconds to also solve. Can you try out this question? I've given you an explanation on how to solve them. Now, if you have solved, like I said, delta H is equal to Q over N. And then N is equal to mass over molar mass, which is 8 gram over 2, because we are talking about hydrogen gas here. So hydrogen gas, the molar mass will be 2. Hydrogen atom is 1. And because we are dealing with H2, molar mass is 2. That's 8 over 2. You have 4 moles. Then our Q is equal to delta HC times N. That's 571.7 multiplied by 4, which is 2287 kilojoules. Note that despite the fact that delta H is negative, if you are calculating for Q does not take positive or negative. Q does not take positive or negative. That's why we are ignoring the negative sign. Take note of that. So you are going to have this. So far, we've been able to explore energetics. We have looked at typically what energetics means. I have looked at we've said is energy changes in chemical reaction. Then if we are specific, if it is heat, we call it thermochemistry, which is the study of heat changes in chemical reaction. And then we said all of them are both under an heading called thermodynamics. They are under thermodynamics. And then we have looked at a major terms used in energetics. We have we have a system, the surrounding, and the universe. I've told you that anything, maybe the container, and anything within a container or an apparatus is a system. And I told you we have 3 types of system: the open, the closed, and the isolated system. And then I said a typical substance undergoing energetics or thermodynamics is defined by 3 things: the enthalpy, which is the heat content of that substance; we have the entropy, which is the degree of the surroundings; and the free energy, which is the fraction of the system that is doing useful work. And I said all of them are state function. They are dependent on the initial and the final state of a system, so they can have changes. So we have delta H. All of them are measured in kilojoules per mole, except for entropy, which is measured in joule per mole per Kelvin. But we typically focused on the enthalpy. This is the heat content, and of course, enthalpy change to be HP minus HR. Then we move ahead to look at standard enthalpy changes. Then we looked at of neutralization, of solution, of combustion, and of formation. We have been able to also look at that the heat of formation is generally dependent on the Elsie's law, which says that the enthalpy of a system is independent of the route taken uh, during the reaction. And then we've looked at exothermic and endothermic changes, especially when it comes to enthalpy. We have said that exothermic is when heat is liberated, and endothermic is when which is exothermic is given as HP minus HR, while endothermic is when heat is absorbed, which is HR minus HP, as the case may be. Then we've looked at heat of neutralization, heat of formation, heat of combustion, and heat of formation of solution rather, respectively, and their respective calculations. So I hope with this you've learned greatly about energetics. Ensure you take more questions and solve on your own. You usually find these questions in your white pass question and especially JAMB for Nigerian student. A lot of questions like this usually come up under energetics. Continue to learn chemistry and bye bye for now. I remain Olusoya Olalekan Adeola Emerald, your best chemistry tutor. Bye bye for now.